All right, so the problem that I saw people struggling with finishing putting together, I really loved that a lot of people saw the completing the square aspect of this problem. But I just want to kind of run through the whole thing, um, and especially look at the part about the stretch factors of the elliptic paraboloid that we end up looking at here. So exercise 3 from the formal written homework for the prerequisite material. Classify x squared plus 2z squared minus 6x minus y plus 10 equals 0 as either a cone, elliptic paraboloid, ellipsoid, hyperbolic paraboloid, hyperboloid of one sheet, or hyperboloid of two sheets. You should look up the generalized equations of these surfaces and then use completing the square to figure out which of these forms the above equation is. Give details in your description as to the orientation, center, and how much the shape has been stretched. So if we go, I'm going to go ahead and post this along with this video. Here is the 6 basic quadratic surfaces that we can look at. So this essentially takes care of every single possibility where you have squared terms available. Actually, well, if you have 2 or more squared terms. So if you have a single squared term and then 2 terms that are of a degree 1, then we'll have some other possibilities here. But this is the 6 forms when you don't have x and y, y and z, or z and x in the same term. So we're not going to, these would be essentially rotations of these different shapes. But if we look at our specific equation here, what we want to note is that there's no y squared term. And the x squared and z squared terms are positive. So if we look at these facts and go through this list, for the cone, we see that all 3 of the terms are squared. For the hyperboloid of 2 sheets, same thing. For the ellipsoid, all 3 are squared. For the hyperboloid of 1 sheet, they're all 3 squared. So if we get over here to the elliptic paraboloid, we see 2 squares and 1 not squared. For the hyperbolic paraboloid, same thing. But for the hyperbolic paraboloid, 1 of the squares is positive and 1 is negative. So we need to be in the elliptic paraboloid scenario. So the difference with ours, though, is that the y term is not squared as opposed to the z term being not squared. What that means is that our elliptic paraboloid is going to open up in the y direction. We'll kind of look at the details of that a little bit more in a second. Let's note that the a, b, and c are the stretch factors. And this comes from transformations, where this is essentially the same thing as z over a equals x over b squared plus y over c squared. If we have it not in this form where I just rearranged the parentheses, but in this original x squared over b squared, we see that the denominator of this is the square of the stretch factor. So we're going to have to get a square root of whatever the denominator is to get the stretch factor there. Let's take a look at this in detail for this specific problem as opposed to just talking about it generally. What we want to do to start this problem is, since there's no y squared term and we're trying to get it to match this form here, I want to get the non-squared term by itself on the opposite side of the equal sign. I'm going to do that with the constant as well. I'll get into why I'm doing that here as I go. So I'm going to rewrite this as x squared minus 6x plus 2z squared equals y minus 10. So I'm organizing it this way so that I can complete the square on the x terms, and the z doesn't need to have its square completed because there's no other z term. And then I'm moving the constant to the other side so I can deal with it separately. And really it's going to be attached to the y here in a second. So my next line, I'm going to write x minus 3 squared plus 2z squared equals, I'm going to pause for a second. So this is x minus 3 squared because when I FOIL this out, I should get an x squared and then a minus 3x and another minus 3x. But what this does is that when I square this, I get a plus 9 that I didn't have. So by switching it to this completed square form, I have now added 9 to the left side, so I need to do the same to the right side and add 9. So the right side now has y minus 1. So this is almost what we want, but we notice that in the form given, we don't have any coefficients to the left of the terms for x, y, or z. They are underneath, so I want to do that. And so I can do this in two different ways. I'm going to talk about both. Actually, before I get into that, let's just note a couple of things that we know now. That this is an elliptic paraboloid. Opening in the positive y direction. And we know it's the positive y direction because it's a positive x squared term and a positive z squared term. If these were both negative, it would be opening in the downward y direction. Just like if I have a basic, I'm going to erase this in a second, but if I had a basic y equals x squared, I know it's a positive opening in the upward direction. Y equals negative x squared would open in the downward direction. So since both of these are positive x squared term and a z squared term, we know it's going to open in the positive direction. So let's get rid of this real quick. Okay. So the vertex is going to be at 3, 1, 0, and that's because we have a shift to the right 3 in the x direction, over 1 in the y direction, and no shift in the z direction. So there's my vertex. And I'm now going to do this in two ways. I'm going to do x minus 3 squared plus z squared over 1/2 equals y minus 1. And when I look at it in this manner, we see that the z stretch is the square root of 1/2, because this is really a squared term, so this is the square of the z stretch. So that's one way of looking at this. Or we can look at this as x minus 3 squared over 2 plus z squared equals y minus 1 over 2. And that's just by dividing both sides of this by 2. And when I get that, I get an x stretch of the square root of 2 and a y stretch of 2. The y stretch is not a square root in this case because the y is not a squared term. So I don't need to take the square root of the denominator in order to understand what the stretch is. So, and in this case, no z stretch. So these two different ways of looking at this are equivalent ideas. They are talking about the same graph. And we can see that, let's see here. If I pull this up on GeoGebra, this is our, why is this not showing? There we go. So the one that has a vertex at the origin, that's our basic elliptic paraboloid. And the first way that we look at our new one is that it has a z stretch of the square root of 1/2. So that means it's been compressed in the z direction by a factor of the square root of 1/2. Another way of looking at it, a different way of looking at it, is that the z hasn't been compressed so much as the y direction has been stretched to the right, and the x direction has been stretched out to the right in its own manner. And it turns out that that is equivalent to having the z stretch of the square root of 1/2 in that direction. So that's really what we're looking for here. Where are we at? So that's what I want you guys to get out of this. For the different kinds of quadratic surfaces, there will be slightly different things. You're going to need to use your algebraic techniques to get through them. But hopefully that this little bit is enlightening and helping you see what needs to happen with these kinds of problems. And know that we are going to readdress this here in a few weeks when we actually start using these quadratic surfaces for finding equations of tangent planes and things of that sort. All right, thanks so much for watching.